Folks, three quick segments to really finish telling the story of the parts of the first four chapters. We're done with 16, and actually we're done with 18. But there's a couple pieces left in 17 and 19 that we still need to kind of wrap up to finish the amount we're going to cover of 16 through 19, at least for now. There's a little bit of chapter 18 that we're going to come back to in, I think, 2 weeks once we get into chapter 21. But that's down the road a piece. For now, just a few short segments, basically about a thing we already know. Ready? Here we go. Suppose, one of my favorite words, suppose we have two plates with each with area A, and we've got them a distance d apart. Suppose they are conducting plates, and we've charged this one to a positive total charge Q, and we charge that one to a negative, same size, opposite sign. So imagine if we're moving electrons, imagine that we take a whole bunch of electrons, put them over here so that this one is total negative charge Q. That means we're short that many electrons, so we're net positive on this side by exactly the amount that we moved. Cool. We already know the story here. We know that there is an electric field E that points from the positive plate to the negative plate. We know its magnitude because Gauss's law is sigma over epsilon, sigma being Q over A. Cool. So far, this is review. This is great. We also know that in order for an electric field to exist, the potential difference between one point and another point d apart in an electric field is given by negative ED, or if we're being really careful, negative E dot little displacement. The electric potential goes up the closer we get to the positive plate. If we start from the positive plate and follow the field ED to the right, E dot displacement is positive because we're going in the direction of the field. But the electric potential is decreasing because we're getting closer to the negative. So we need that minus sign. If we start from the negative plate and go this way, we're traveling opposite the field. So this dot product gets us its own negative sign, which cancels this one. And the potential difference as we look this way is positive, exactly like we'd expect. Cool. So the potential difference, negative to positive. So like, for now, let's just talk about the magnitude. How big is the electric potential difference from one side to the other of this arrangement? Well, if we're taking the absolute value, we don't need the minus sign. We just need the electric field times the distance that we travel, d. But we know the electric field. It's Q over A epsilon times d. So I'm saying that the size, the magnitude of the electric potential difference from one side to the other of this arrangement is this expression. All right, cool. So suppose I solve cross divide for the ratio Q divided by potential difference. Total charge on a plate divided by the potential difference between the two plates. We got to cross multiply and get this stuff over here. A epsilon over D. So far, we're just moving stuff around we already knew. But here's the thing. Those parameters, the area of the plates and the separation distance between them, it's all about geometry. What's the size of the plates and how far apart did we put them? This parameter epsilon has to do with what material lives between the two plates. In this case, we're saying it's just a vacuum. The permittivity of free space, epsilon. What is this thing in the red cloud equal to? Well, it's the ratio of the charge to the potential difference. So, sorry, hold on. No matter what we do, no matter what Q is, no matter like whatever we do, the ratio of the charge on a plate, in other words, the amount of charge we had to move from one neutral plate to another neutral plate, right? We take all of these electrons from this one, put them on this one, and now they are plus Q and minus Q. How much charge did we have to move to get it this way? And what electric potential difference are we setting up by doing that? Because just by having the charge on the plates, we know we've got an electric field. And if we have an electric field a distance d away, we know that there's a potential difference. So move some charge, and the ratio of the charge that we move to the electric potential we had to we set up by doing that is constant. Constant and depends only on the geometry of the situation. That is pretty cool. For how are we going to move charge? Well, we got to set up an electric field. We actually have to push charge to do that. Let's see, what color am I going to use here? I'll use orange. In order to get electrons, well, let's talk about a battery. In order to get positive current to flow this way, we need a battery here. And in order for the energy to be conserved, the energy associated with the battery, in other words, the potential difference associated with the battery, needs to be the potential difference that we need to set up. So that if we can imagine a kind of a circuit loop, the positive potential difference this way and the negative potential difference this way are equal, because we're moving, it's sort of almost like we're moving charge through a circuit. So this battery has some voltage, some potential difference associated with it, and that potential difference is the potential difference that we need to move a charge Q from one plate to the other. To move a charge Q from one plate to the other to set up an electric potential difference having to do with the electric field that we create by having positive and negative charges separate from each other. This potential difference and this one are the same. How much charge Q can we move? How much charge Q can we arrange to account for this much potential difference? To how much charge can we move using a battery with this much voltage? This much, the red cloud much. How much charge do we need to move, or can we move, per battery voltage? We're going to move the charge from one place to another, and we're going to kind of keep it there, because now that we've moved it, take away the battery. And just now we did a bunch of work moving charge. And now it's done. It's there. It's like it's I don't know, it's like it's stored almost. If we connected these two plates again, just, with a wire, the positive charges here would repel the other positive charges and it would move back this way. There would be a current flowing this way. That current moves charge, and that moving of charges is doing work. How does this arrangement have energy with which to do work? Well, we just did a bunch of work on it with the battery, and then we stored that energy in this charge configuration of parallel plates. How much charge Q can we store for a given voltage of battery? This much. So this is storage capacity. How much charge Q can we store in a sort of plate separated arrangement like this by doing work associated with a battery voltage? This much. Storage capacity. Let's define this to be capacitance. Actually, you know what? Let's define this to be capacitance, the ratio of charge to the potential difference we needed to separate, to move that much charge and keep it in a configuration like this. For this kind of configuration, we already have the answer. What is the ratio of charge to potential difference? So the product of the area, the permittivity, divided by the distance. Capacitance. Let's use a capital C. This is a variable, not a unit. This is not coulombs. This is capacitance. The variable that we will use is capital C. What are the units? Well, apparently, if we look at this expression here in the cloud, we've got meters squared divided by meters. Now, epsilon. Whew. Electric field, I don't remember the units for epsilon. Wait, yes I do. Epsilon is 1 over 4 pi k, right? So k was Newton's Coulomb squared, Newton's meter squared per Coulomb squared. So epsilon is the upside down. Coulomb squared per meters squared newtons. Yuck. Okay, what even is this? The meters squareds are going to cancel. So we've got Coulomb squared per meter newton. Gross. Okay, well, suppose we separate coulombs. Newtons per coulomb is the upside down of field, and meters in the denominator is the upside down of meters. This is coulombs per volt. Yeah, okay, I guess we knew that. Q per potential difference, coulombs per volt. Coulombs per volt. Let's define that to be a farad. This is named after Michael Faraday, whose work with currents that change we will talk about in a later chapter. The unit for capacitance we name after Faraday, and we shorten it a little bit, so the unit for capacitance is farad. Capital F is our symbol for the unit. Capacitance, capital C, not coulombs. This is coulombs because it's showing up in the curly braces. That means I'm talking about a unit. Cool. So, again, we take our two neutral plates, we attach a battery with some voltage, and we can move charge using that battery. But eventually, there's enough charge built up that the field created by that charge pushes back on whatever new positive charge we would try to move, pushes back equally strong. That, some other charge here living in this wire feels an equal force. The battery's trying to push it, but the field is trying to push it back, and it gets stuck. And there's a limit to how much charge we can move. Great, so we move this much charge. Let's disconnect the battery. Now these are fully charged. If we move them together, what happens? If we move them closer together, this thing in the red cloud, the effective capacitance of this kind of arrangement, move them closer, it increases. But the charge is what it is. We put extra charge on this plate, and we haven't removed any, but we haven't added any either, not by pushing them closer together. The other thing too, this field is as strong as it is according to Gauss's law. We haven't changed anything about that. The charge density is still Q over A. So the electric field E hasn't changed either. Charge Q hasn't changed, but this is increased. That means delta V must have decreased. The effective potential difference between the two plates must decrease as we push them closer together, which means if we pull them farther apart. Now, and that makes sense, right? This is positive charge, and this is negative charge. They want to go together. They're attracted to each other. If we let them get a little bit closer, that's a lower energy state. That's a lower electric potential. It makes sense. If we pull them farther apart, we're increasing D, which decreases the capacitance, but that means that the voltage has to go up. Because again, we're not changing the charge. Cool. Okay, so I said a minute ago that this was a charge configuration that lets us kind of store the electrical work we did to move charge from one side to the other. How much energy have we stored? Here's a quick proof. Capacitance is Q, the electric potential that's between the two plates. If we solve for Q, C delta V. Each time we increase the potential difference across the plates, we can store a little more charge. Q is a function of potential difference. The bigger the potential difference, the bigger the charge we can store. Now, work is Q times delta V. Suppose we move these charges electron by electron. Each time we do that, we increase the potential difference slightly, and we have moved slightly more charge. But each time we do that, the electric field changes. So each time we do that, it takes a little bit more work because we're trying to push it through a greater and greater and greater and greater delta V. Every time we increase delta V, we've got a bigger and bigger and bigger change in the electric potential environment that we have to move that electron through. Every time we do that, we do work with a bigger and bigger and bigger ski lift until the battery has exerted its maximum capability, and that's the tallest the ski lift will possibly be. Every time we move a little bit of charge, move a little bit of charge through a potential difference. Move a little bit of charge through a potential difference. A little bit of charge through a potential difference. And each time we do that, we're doing a little bit of work. Q times delta V. Each time we do that, we do a little bit of work. How much charge? This much charge. How much voltage? This much voltage. This little bit of change in voltage. Because we got to move a little bit of charge through that much voltage. A little bit more charge through that much voltage. Through that much voltage. Each time we do this, the voltage gets bigger, and we move a little bit of charge. The work that we're doing is going to be this triangle. What's the area of this triangle? It's 1/2 base times height. It's a triangle. The base is delta V big. The altitude, how much charge have we moved altogether? Well, Q here is the capacitance times delta V. So this value is C times that same delta V every time. Another argument, and I think this is the one the book gives. I like this one because it actually points us toward calculus. It's not calculus, don't worry, but it sort of points us towards calculus, which I like. The other argument is that we start with uncharged plates. We're going to charge them up all the way up to a final voltage V. That happens linearly. On average, the voltage is half of that. So half of Q times, oh, see, wait. Hold on now. Yeah, this is Q. It's half of Q times delta V. We're moving a total charge Q through an average voltage of half the total. So here's half the total, and there's your total charge Q. So we've got half the total charge on one plate or the other times the potential difference we're setting up. And that's an entirely equivalent way to write the amount of work that we did to set this up, the amount of energy that is stored. All right. Let me go a little bit farther. If that's how much energy we're storing, the potential energy stored in a capacitor, 1/2 capacitance potential difference squared. Now, the potential difference that's E times D. Because we're squaring it, so it doesn't matter whether it's positive or negative, it's ED squared. If we're talking about a parallel plate capacitor like this one, we know the expression for the capacitance. It's area epsilon over D, E squared D. All right. The D's, one of the D's cancels. So we've got 1/2 epsilon E squared AD. But the cross-sectional area A times the distance between the plates D, that's the size of the volume here. We've got an area stacked D wide. That's a volume. I'm not going to write capital V for volume because that's confusing. We've got V's all over the place here. I'm just going to write volume. So the way this is usually reported, we talk about the potential energy stored in a capacitor per unit volume as 1/2 epsilon E squared. You could call this the energy density because it's energy per volume, like mass per volume is density, right? So this is the energy density really of the electric field because that's the only thing over here. Electric field energy density, and we did work to move the charges, but the charges themselves set up the electric field E. So you can almost think of it like the electric field that we set up by moving the charge is the thing that stores the energy that represents the work that we did to put the charge in this configuration. Energy density of an electric field goes like the square of the electric field strength. Cool, cool, cool. Cool, 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 cool. There's one last piece to chapter 17, and it's really not bad. The other formula that we wrote is the capacitance for a parallel plate arrangement, like this one. What if we put something else between the two plates? The bigger the capacitance, the more charge we can move for a given battery. So is there a substance with greater permittivity than free space? And the answer is yeah, of course. We could use styrofoam. We could use paper. We could use even distilled water. And they would all have a greater permittivity than free space. Now, free space is like the baseline. I care about how much more permittive whatever substance you're going to put in there is than free space. The way we keep track of that, we express the permittivity of whatever we're talking about just as epsilon, not epsilon sub zero. That's for free space. Not epsilon sub zero. That's for free space. Depends what we put in there. What is the permittivity of the thing we're talking about? And the trick is that we express it as a factor, as a multiple of the permittivity of free space. How much more, by what factor is this substance more permittive than free space? The way we keep track of that is with a Greek letter kappa, which sort of looks like a capital K. I kind of tend to exaggerate the difference. If I want the letter K, I'll just write it, we said that, we've got K, Q over R squared. And I try to sort of push the fork of the K close to the bottom. And for kappa, I try to push the fork close to the top so that it's clear what we're talking about. Like I said, the textbook can do all kinds of neat things with typeface and junk, but on the board, this is what kappa is going to look like. And the name for this, that's the symbol. The thing that we're representing with the symbol kappa, we call it the dielectric constant. And it's a thing we look up in a table. So for example, free space equals 1 times the permittivity of free space. So its dielectric constant is 1. Okay. That's chapter 17. We're done. Well, done with chapter 17. On to the next segment.